Hi, today I'd like to talk about what happens to particles as they bounce around at random in an environment. Okay, as particles bounce around at random in an environment, if there is a disturbance, that disturbance is going to propagate out at a certain speed. Now, the speed at which that disturbance propagates is actually related to the average velocity of the particles as they bump into each other. Because the fastest rate at which it can transfer that information downrange is the rate at which it can either travel downrange or bump into another particle and send the other particle downrange. Okay, and so the average speed of the particle is often related to the energy, where E is equal to half mv squared. So the energy of the average particle is going to be equal to related to the mass of the particle and the velocity squared. Interestingly, the temperature is proportional to the energy. Not exactly equal, but proportional to the energy, which means it's also proportional to the average mass of particles and the velocity squared. So now to find the velocity of the particle, I'm going to go ahead and divide by the mass and then take the square root of that. So I know that the velocity is going to be proportional to the square root of the temperature divided by the mass of each particle. And so now this rate at which the disturbance can propagate downrange among these randomly moving particles is known as the speed of sound in an ideal gas. And this is why the speed of sound in air is directly related to the square root of the absolute temperature, normally measured in Kelvin or Rankine. And it also is essentially, it's also related to the molecular mass of each particle, in that the lighter the particle, the faster the speed of sound throughout the medium. Okay, so basically hotter air transfers sound at a faster speed than colder air. And also, if the particles in a cavity are in a cavity and the cavity has a certain wavelength that it favors, okay, we know now that the frequency is equal to speed of sound over the wavelength, where the f is a frequency, a is the speed of sound, and lambda is a wavelength. Now, if lambda is constant, then we know that the frequency is going to be directly related to the speed of sound. And this explains why people speak at a higher pitch when they breathe helium, because helium has such a very low atomic mass that the speed of sound in helium is much faster than it is in air of the same temperature. And so the faster speed through the helium, combined with the essentially the faster speed of sound through the helium, means a higher frequency. And that is why, as I said, people speak with a higher voice when they breathe lighter gases. Now, there are some cases where the disturbance is so powerful that it can actually compress the gas enough to actually change the temperature, in which case the sound itself affects the speed of sound. Okay, and this actually opens up a whole new branch of physics, which we often know as non-linear acoustics. Anyway, that is all I have for now, and thank you very much for watching.